So he's a PhD student. I know that guy. Which guy? African speaker. Oh, really? How do you know that guy?
Because of music and art,
I think he used to live in Spain. So he's also a PhD student. So many PhD students. I mean, Australia makes a big part of the government, federal government, so I think annual GDP for the
80,
What research are you doing on snakebite bandit and green the very interesting. Very in 5 countries. Yeah, I'm in 5 countries. What is something? Yeah, it's so cool. Oh my god. Oh no, I'm not doing anything, but I'm like, hello, woman.
Like in humans, do you do anything in animals as well, or is it just humans?
Not just from the hospital clinical practice. Yeah. I have to ask medical doctors how they practice. Yeah, how they various.
That is really cool.
Yeah.
Wow.
Yeah, very cool stuff. And then she tell me, oh, I don't know, oh, I'm gonna leave it. Why?
It's stressful.
She's also from Malaysia.
Yeah, from Malaysia.
But she's been here very long, many years.
Yeah, over 10 years, yeah.
10 years. You 10 years? No. No, 5 years. 5 years.
Hello. Hi everyone. Thank you for joining us tonight and welcome to Raising the Bar Adelaide. Before we begin, I'd like to acknowledge that we're meeting on the traditional country of the Kaurna people and pay respect to elders past and present. We recognise and respect their cultural heritage, beliefs and relationship with the land. We acknowledge that they are of continuing importance to the Kaurna people living today. Thank you to the Maylands Hotel for having us here tonight. Just some small housekeeping. The toilets are located to the left of the bar. Food and drink are available throughout, so please order up, help yourself. We're very excited to have Albert Rajkumar with us here tonight to present to you how do you build a city on the moon. For those of you who have not attended a Raising a Bar Adelaide talk in the past, welcome. This initiative was started by a couple of university students in New York who thought it would be cool to turn pubs into a classroom for the night. This event has been held all around the world, from Hong Kong, London, Auckland, San Francisco, Sydney, and more recently Christchurch. We're proud to bring it to Adelaide for the 9th year. We hope you enjoyed this evening's talk, and we encourage you to support the speakers and share your experience via social media by tagging @CityofMPSP. Thank you again for being here, and I'll hand it over to Albert.
Thank you. Excellent. All right. Thank you. Thanks everybody for coming out here tonight. Well, I see a lot of familiar faces, some of them, a lot of new ones, but I'm assuming that some of us, if not most of us, know what we're going to be talking about here tonight. Building cities on the moon, humans and robots working together, extended reality. And so, what do all of these things have to do with life back here on Earth, right? And so, if you didn't know that before, well, now you know, thanks to our lovely MC. But before I get into that, I just want to talk about something that I realized while preparing for this talk. So, it seems to me that we're all, in our daily lives, entangled with automated systems already. Now, we don't really pay attention to this relationship that we share with these automated systems, but nevertheless, it sort of it manifests into our lives every day now. For example, me and my wife, Deepa here, we love going on e-bike rides. So we take our e-bikes out, we pedal, we steer. The e-bike, it assists us so that we don't have to work so hard, right? And I'm sure many of us used Google Maps to get here tonight. And Google Maps, what do we do? We put in a destination. and Google Maps tells us where to go, keeping in mind the turns and the traffic. But eventually we decide where to go, how to go, but part of the process, the decision-making process, has already been offloaded into our phones, right? And I'll give you another example. Let's say autocorrect. We type something, it tries to predict what we're trying to type. Sometimes it's a good word, sometimes it just replaces a word with just something that makes it sound completely unhinged, right? And so I'll give you one more example. Like me, I'm sure many of us in this room have a robotic vacuum cleaner in our house. So we don't control every inch of the movement of a robotic vacuum cleaner. We just tell it to go do some broad tasks like go clean the kitchen floor, right? So it handles the task relatively well until it gets stuck under the table or it eats a cable and then it asks me for help. Now that's usually in the form of a notification that I get on my phone. Alright, so why am I telling you all about all of this? All these systems, they're not robots in the same sense, right? That much all we can agree on. But they're all some form of automated systems. And the way that humans and robots and these machines, we interact, they lie on a spectrum. So in some cases, we do most of the work while the machine just assists us in some way. And in some cases, the robot does most of the work, and then we just get involved when something goes wrong. And so we find ourselves that we, in our everyday lives, are already working with robots or machines every day in our lives. But my research interest My research interest has to do with how, when these situations are taken to high stakes levels, like construction on the moon, right? And when the human is taken far away from this robot, how can we deal with these situations? And so I want to talk about space flight, because space flight has been dealing with these kind of issues for a long time. You may have noticed that I put up something on the board. This is the Skylab, the space station Skylab. Sir, do you remember Skylab? Let me ask you.
Yeah.
You do? You do? Yes, so Skylab, right, was the first, let's not talk about that part yet. Yeah, so Skylab was the first American space station, right? It was launched all the way back in 1973. So when it was launched, it did not have any crew on board. It was launched empty. But what happened during launch was that the heat shield, it came tearing off. So it had two solar panels, one of them broke off and the other one got jammed. And so what happened was NASA, they had only a couple of days in order to try to figure out what happened and how to solve this issue. Eventually, when they launched the astronauts a couple of days later, what happened was they were able to deploy this golden thing that you see here. It's a solar shield, it's a heat shield, so they had to deploy it like an umbrella in order to prevent the space station from overheating. They were also able to, if you see, they were able to deploy one of the jammed solar panels. And so all of this was possible because we were able to collaborate among different aspects of the whole operation in order to sort of salvage what was there. All right. That's the incident with Skylab that I wanted to talk to you about. But Skylab also teaches or talks to us about architecture in space, or space architecture. Now, what I find interesting is that, yes, Skylab is a tin can, right? It's a pressurized can inside which there are facilities like dining spaces, places where we can eat, drink, sleep, work. But it's more than that, in the sense that it has solar panels, it has air circulation systems, one of which fails and we're in deep trouble. Right? And so this is probably a good time for me to talk to you what I mean by space architecture. Space architecture is defined as the theory and practice of designing and building inhabitable volumes outside of the Earth's surface, so beyond the Earth, right? So we do think about rooms and tables and all that, but we also have to think about things like how do we construct these things? What happens when things go wrong? How do we maintain, repair? How do the people inside, how do we keep them sane, like physically and mentally in check, right? And what happens in times of a medical emergency, for example? And so that's the space architecture we talk about. Let's talk about something else. This is Space Station Mir. Now, do we remember Mir? We do, right? So Mir was the Russian equivalent of Skylab. It was Russia's Skylab. So the incident that I want to talk to you about Mir, 1997, what happened? What happened was an astronaut, or a cosmonaut rather, was on board Mir. He was trying to dock a resupply ship onto his space station. Right? He was doing that through a video screen, and he had these joysticks, and he was trying to dock it. The space station, the spacecraft, it came in too hot. He could not judge the distance and speed properly. It hit Mir, and so it sent Mir into this. It sent it into this like spiral. Right? It got so bad that one of the modules got depressurized, and so eventually they did manage to bring it back to normalcy, but and there were a lot of causes for these problems, right? But one of the problems that is directly relevant to our talk tonight is the fact that it is extremely difficult to judge the speed and distance of something when you are looking at it through a 2D screen. Right? So that's the part I want to talk to you about. After Mir, we have the International Space Station of today, right? So that International Space Station, or ISS, has been in operation since, I don't remember the exact date, but it has been a long time. Continually, it has been assembled, it has been repaired, it has been repurposed, like moved around. And so space architecture is filled with things like this, filled with things breaking, jamming, leaking. And so when we think about a lunar city or a lunar settlement, I think we should not think of a lunar settlement as something that is sparkling, you just like put it there and it magically works forever. Rather, I think we should think of it like Mir or space station, where we have to look at it as a complex system that we have to continually manage, like resupply, repair, maintain. And so, so we can conceptualize what all of these settlements can look like on the moon, right? So we can prepare for it, we can design it. But also I think we need a way to prepare for all these things that might go wrong on Earth. So how do we do that? How do we practice for all of these things which might go wrong? And that brings me to the next part of my talk that I want to talk about, which is something called space analogs, right? So before I get into that, let me just put up a okay. All right. So when we want to study about space, we cannot recreate every single condition that outer space has, right? So what researchers tend to do is we tend to isolate one specific condition or space that they want to study, and they recreate it in facilities like this, and they're called analog facilities, like I said. And so this facility, for example, its name is the Human Exploration Research Analog, or HERA. So this is based in Houston, Texas. Scientists over there, NASA, use it to study things like isolation, confinement, and all these things. Right? And I had the yeah, I was really excited to actually visit this thing back in 2018 or 19. So when I was there, we got to go inside, and inside it was a fantastic experience. I had a lot of fun, but I remember feeling like, this space is a little bit claustrophobic. It's small. There's like metallic things all over, shiny. Everything feels sterile, and there's no like soft surfaces, no carpets, no pillows. And so for me, only in that 1 hour or so, already I began to feel the heat, so to speak, right? But imagine NASA, they lock people in here for months on end, like 4 months, 5 months, 6 months. For them, just the simple act of like having a beer or sharing a plate of chips, that becomes a challenge by itself. So this is HERA. I want to talk to you about another kind of analog facility. This one is quite interesting too. I promise this is not AI generated or not from a movie. This is a thing called NEMO. So this thing exists off the coast of Florida, right? 60 feet under the surface of the water. On the reef, they have this underwater experimental laboratory. NASA, they test things like confinement, again, but also they test things like protocols for spacewalks. How do they do that? They put people into diving gear and they make them do spacewalks on the reef. Right? And so they see what can go wrong. And so it's interesting to me sometimes, in order to be an astronaut, you have to be an aquanaut first. That was something that I realized. So we have these kind of things. There are more analogs, of course, in the world. Some are in the middle of a desert, some are on top of a mountain, some are in the middle of a volcano. But all these analogs have one thing in common, which is that they're trying to isolate that one condition of space, one or more, and they're trying to study it so that they can be better prepared for what is to come. Right? And so what if we think about that? We can prepare as much as we want for what is to come. But when we actually go to the moon, when we find ourselves on the surface, how do we actually construct things? How do we make sure that the things are put in place already? So let's talk about that. But before I get into that, I want to talk about a little bit of the environment today. What space agencies are doing today. So, space agencies and private companies, they're talking about sending people to the moon, back to the moon for repeated visits nowadays, right? You might have heard about Project Artemis. Artemis program, have you heard of it? No? Project Artemis is the equivalent of the Apollo missions, right? So Project Artemis is of today. What NASA is doing is they're leading this group of nations and saying that let's go back to the moon, not just for a simple visit, but for a sustained presence, a long-term presence. And so that's Artemis. Recently, only only in this year, they launched something called Artemis 2, where they sent 4 people around the moon and back. So they were testing this thing called the Orion spacecraft, testing how if it actually manages to keep these people alive or not. And so with this Artemis 2 project, what happened was it was the first time in more than 50 years that any humans went back anywhere around the moon. Right? The last time that we went was, I think some of you remember this, 1972, when we had Apollo 17. That was the last time we had humans on the moon. And so I want to talk about a little bit about what is the difference between Apollo and Artemis. Like I said, Artemis wants a more sustained lunar presence. Apollo was more about quick visits and experiments and then coming back shortly. Well, there is another thing. There is China. China is leading its own group of nations in order to build something called the International Lunar Research Station, ILRS. And so I do feel like there's a space race of today going on nowadays. Space race 2.0, you can say. But I do feel like there's also a lot of things which are different this time, right? And I say that because, yes, we see a lot of competition between these countries in trying to see who can establish themselves on the moon for a longer period of time this time. But we're also seeing a lot of collaboration between governments, private companies, universities, in order to see what we can do on the moon this time. And so today's push into space, I think it's more about commercialization. Because private companies like SpaceX, Blue Origin, these companies are developing launch capabilities, so the rockets which are going to take us from the Earth to the moon. They're also developing landing capabilities, so the things which will bring us from the lunar orbit down to the lunar surface. Right? And so there is one more company that I forgot to mention, which is Astrolab. This company is building lunar rovers so that first we can move around. We have surface mobility on the moon, but then they will also allow us to build on the moon, right? Soon, very soon. And so, for building stuff on the moon, for building this infrastructure, NASA, what they're doing is they're actually planning to send robots first on the moon to prepare for the humans' arrival eventually. So, let's take a moment to think about that. And I'd like to think about something that happens here on Earth, an Earth analogy. So, let's say a human operator, a construction worker, is working an excavator, let's say. Right? What happens? The excavator so the human sits inside, and they are operating, so they're able to hear, see, feel things. They can turn their heads around to sort of understand what the situation is. But imagine if you remove that operator away and just make them control the machine through a video screen, right? So that is called teleoperation, where they are operating, they're in charge of operating the machine directly still, but their experience of this whole event has been reduced to whatever they can see through the video screen, right? And so imagine that we give this machine more autonomy. So instead of directly controlling the machines, now you're able to say things like, hey, go dig a trench from here to there, or build this section of the wall, right? So now in this scenario, the machine would carry out most of the tasks, and the human's job would be to just sort of gather information and intervene when something goes wrong. Right? So this is supervised autonomy. So why did I tell you about all of these things? It's because I think that for us to have a more sustained lunar presence, I think the shift from teleoperation to supervised autonomy, it's unavoidable, right? We can't spend each and every minute just like looking at robots all the time. So when we talk about this, we can understand that we have the robots working, we have the humans awake. And just like what we discussed with the collision with Mir, space station Mir, it's very difficult to judge the distance and speed of things. So we are beginning to understand that when we take all of these problems on the moon, it's going to be very, very difficult, right? Because on the moon there is absolutely or almost no atmosphere to scatter the light. Things that we take for granted here, right? So the illuminated areas will appear extremely bright. The dark areas are going to be pitch black. So with this, it may be very difficult to, or it may be very easy rather, to miss some important detail. So we arrive at this strange kind of construction worker who is nowhere near the robot that they are working with. They're not teleoperating it, they're kind of supervising it. So this is kind of the research that I found myself into here in Adelaide. Right? But before I go further, I'd just like to take a sip because my throat is parched. Okay. So that's the research that I found myself into. But I did not grow up obsessed to be in space, or I did not grow up idolizing astronauts, for example. So how did architecture students back in India come to be in a place like this? So that's what I want to talk to you a little bit about next. So during my time, let me just check if I missed out on something. Okay. So during my time as an architecture student back in India, what happened was there was a period in my life where I got disillusioned with architecture. I just couldn't see a way where I could graduate and meaningfully contribute to society. I just did not want to build yet another concrete building. And so I remember thinking at that point of time very vividly that I don't want to be just another brick in the wall. And so that line has become slightly ironic now because I spend a lot of time studying bricks actually nowadays. But yeah. Okay, so this is where I was. My salvation came when I discovered space architecture, right? So suddenly I found a way where I could contribute meaningfully to life. This sort of desire to contribute, it took me to Houston, Texas, where I studied space architecture. And when I was over there, I met the head of lunar architecture research, Amit Srivastava, who is here tonight. Amit became my supervisor, and he brought me to Adelaide in order to pursue my PhD over here in 2023. Right. So, once I reached Adelaide, I found out something. But before I tell you about that, let me just talk to you about this. When I was in Houston, I was involved in a lot of projects that was NASA related, one of which was this thing right here. It's called Project Olympus. Project Olympus, what it is, for you over there, Project Olympus was basically NASA wanting to understand, okay, we want to build things on the moon, sustain long term, so what kind of things do we build? landing pads, roads, habitats, radiation shields. So all these kind of things we were discussing, we were exploring. And we were doing this from the lens of how can we large scale 3D print all of these things? How can we use large scale 3D printers to build all of these things? Now, when I came to Adelaide, I found out that we had a slightly different viewpoint towards this. They were opposed to this idea of large scale 3D printing. Instead, the idea was that we want to use bricks and these modular components, right? The idea was that when it comes time for repair, be it through a micrometeorite strike or a robot colliding, when it comes time for repair, it would be easier if we use bricks and these modular components instead of large-scale 3D printing. And so, yet again, I found myself in the midst of bricks. Right? And I remember why was it that I was so afraid of just being another brick in the wall. And so it turns out that the bricks themselves feel the same way. They don't want to be just another brick in the wall themselves. I say that because there's an American architect, his name is Louis Kahn, and he has this famous quote. It goes something like, even a brick wants to be something, an arch. And so with that, I think what he was trying to do was he was trying to provoke a sense of curiosity in us that even these mundane things in architecture that we take for granted, like bricks, right? They have aspirations. They can contribute so much more in our architecture. And so he was talking about these earthly bricks, of course, but how are these earthly bricks different from lunar bricks? I kind of want to talk to you a little bit about that. So it's very interesting because on Earth, the things that we take for granted, like these bricks, they are ultimately tied to centuries, if not millennia, worth of traditions, bricklaying traditions, right? We have to place them brick by brick by expert bricklayers, and we have to do all of this in Earth's gravity condition. And so on the moon, it's going to be very different. Well, first of all, as I'm sure a lot of you know, that the gravity on the moon is just 1/6 of that on Earth, right? And so that is there. And we don't want to be doing things like we don't want to use mortar because that's more mass. We don't want to use things like scaffolding to scaffold the bricks or to support the bricks temporarily because that is more mass, and we don't want more mass because it's more money. It takes more effort to launch things, so we're trying to minimize. So gravity is low. We don't want to use mortar. We don't want to use scaffolding. And so these lunar bricks, they may be made of the lunar soil, but they have to perform, or they actually have the opportunity to be much more interesting than what we consider a mundane earthly brick. All right. So once we started thinking about these bricks, that got us to thinking about joints. What are joints? Joints on Earth are simply the place where two bricks meet. But on the moon, we realized that joints can be so much more than just where two bricks meet. They can enable the robots to make the bricklaying process easier. They can enable the fact that we don't want to use mortar, so they can enable us to take mortar out of the picture. They can enable us to take scaffolding out of the picture. And so once we started thinking about joints, that got us thinking about the next thing, which is alignment, or self-alignment. Now, what do I mean by that? Suppose a robot arm places a brick, right? And we can safely imagine that it's never going to be able to place every big brick mathematically precise all the time. And so, with this self-alignment of the bricks, we can imagine that the bricks slip and slide into place while the robot places a brick approximately. Right? And so it enables our architecture to be firm, to be robust, even though we have robots which are not precise. And so when we think about all these things, alignment, joints, bricks, when we started thinking about all these things, we began to think about lunar construction in a certain way. That it should be something different to what we think of traditionally. I want to talk to you about what we think of traditionally. Traditionally, we think of these human-robot collaboration as a two-part system, right? It's a dance between the human and the robot. But in construction, there's always this third thing, the thing which has something to say. It's the architectural artifact, like the brick, right? So the brick has something to say in this conversation. And so we thought of lunar construction as this three-part system where the robot executes the task, the human supervises the task, and the architectural artifact, it determined or helped determine whether things would fall apart or whether things would settle into place and all this. And so we came to this idea that it's a three-part system, right? But again, we have to remember that the idea was that we want to take the human out of the system because NASA is planning, in their plans, they plan to have a lot of uncrewed missions and they want to have a lot of, they understand that astronauts' time on Earth is very valuable and it's a super demanding task for astronauts to do moonwalks and perform functions. It's a very demanding task. So we wanted to take the human away from the task, whether it be on the moon or on Earth. So, but remember that what we experienced with Mir earlier, with the collision of Mir, when we take the human away from the situation, there's this reduced situational awareness. So they can't really perceive depth or speed that well, right? And so, so we're thinking of using something to address this issue, and that something is extended reality. Right? Extended reality is what we were thinking that, okay, maybe it helps the human have a better sense of spatial understanding of the site as compared to just looking at a normal 2D screen. Right? So that's where extended reality came in for us. And so to test out this idea, we ran something called SideQuest, which I'm about to show you something. Yeah, I hope everybody can see that. SideQuest. SideQuest was a mini competition that we ran inside of the Australian Rover Challenge, which happened all the way back in March of this year. So in SideQuest, we asked participants to put on a VR headset. When they put on the VR headset, they would have been transported to a virtual lunar office. Right? From the lunar office, they would supervise a robotic arm whose job was to stack some blocks. And so this idea that the human is using XR to supervise a remote construction task, that was the whole idea behind it. Now we gamified the whole thing, so we had like these, okay, before I forgot to mention that the aim of this whole thing was to get the robot, was to work together with the robot to stack blocks as high as you can and in least time as possible, right? So it was a competition, and so because it was a competition, we even had like a live leaderboard. Unsurprisingly, a lot of people kept on coming back just to get one more try, get their name one spot up, one spot up. So that was very interesting to see. But like I said, behind this game, it is the same task of remote supervision of a construction environment. Right? And so once we had this, the next logical question for us was, wait a minute, does extended reality actually help compared to using a 2D screen? So in order to test that, this idea or this question, we come to the next part of my research. Okay, so where was I? Yeah, so does extended reality actually help compared to 2D screens? And so to test that idea, we are planning to run my next phase of my research, my experiment. So this is going to happen in Roseworthy. We have Adelaide University has our campus in Roseworthy. And over there we have a lunar analog facility called Crater. Inside of Crater, we're gonna make a robotic arm. It's quite tall, taller than us. We're gonna make the robotic arm perform some construction tasks. It's gonna go pick up something and do some construction. But it's not going to build everything precisely. Like we said, we want to simulate a robot which is not very precise. And so sometimes the robot will place the bricks in a slightly misaligned position. Sometimes it will be perfect. The participant's job is to sit outside somewhere. They have a caravan where they can sit, and they have to remotely supervise this construction task. Now, they will be using two interfaces. One is a traditional 2D interface. The other is a VR headset. And so we're trying to understand, does VR actually help compared to 2D screens? Because when we run the experiment, we may find that there's no single obvious answer to questions like, should you allow the construction to continue or should you pause the construction? There may be more than one obvious answer. And so XR may end up helping us, or it may also end up providing distraction. So these are the things that we're trying to understand through this experiment, which is going to happen in October, by the way. And I might add that we are looking for participants in this space. So if you're a construction worker or analog astronauts, any astronauts here in the house, I call upon you if you're. Where was I? So we're running this experiment. And you can imagine that this is not really something. It's not a simple experiment. It's a complex part where many people have to come together. So we had to get people from architecture, robotics, psychology, everyone to come and help us. And so we found that in Adelaide, because we found a very good mix of people, research interests, and facilities like Crater in order to help us put our ideas to life. Right? And so we have many. I just want to talk about people which is enabling this research. We have a center called the Andy Thomas Center for Space Resources, which provide facilities like Crater. We have AI for Space and AIML, which is Australian Institute of Machine Learning, who's providing the robot. We have other people in our immediate surrounding, like my supervisory team, for example. Amit comes from the world of architecture and space architecture. We have Anna Ma Wyatt, who's from the world of psychology and perception. We have Edward Palmer, who's from the world of education, VR, AI in research. And so, apart from all these people, we have all these facilities enabling us to do this research. We have something called the Lunar Construction Group also, who are doing research on what should come before architecture, like how to do lunar soil testing or how to develop lunar bricks, for example. And so let me sort of try to wrap up everything with this. At the beginning, I talked about Google Maps and autocorrect and e-bikes and all that. And so all these things, again, I want to reiterate that they have the same relationship, that we share the same relationship with robots, that in one sense, we provide our intent and the robot executes, right? And so, I want to say that the same kind of collaboration also exists in high-stakes settings like mining, underground mining, for example, where the stakes are much higher and mistakes might cost money, time, and maybe even loss of life. And so, when we take all of these things, it may become overwhelming, but I want to say that small steps in order to understand these questions, the big questions, like how do you build a city on the moon? It may sound like a big question, but steps that we take to start answering these questions, we can begin with small things. It may be small things like just adding a new camera or just changing the shape of a brick, you know. So those are the small steps that we can take in order to start solving these big problems. Because in this world, we have to learn. We have to learn how to live together with robots and machines. Humans have to learn how to live together with robots because we have to build a better future together in today's world. And I'm going to end with that. Thank you.
Thank you, Albert. I'm just going to give you this as a little thank you from us.
Thank you.
Does anyone have any questions at all for Albert today? Oh, wait.
Okay. Hi there. My question is, when you're doing all these experiments on the construction and VR and all that stuff, do you include a signal delay? Because it's not instantaneous signal between Earth and Moon.
One point something.
All right. Thank you so much for your question. Yeah, that's a very interesting question because the Earth and the Moon, as you know, is really far away, and for a signal to travel, it takes 1.3, let's say 1.3 seconds one way, so 2.6 seconds if you want to send something and return back. So do we include a signal delay, sir? We don't include a signal delay. Because like I said, we are trying to isolate some conditions that we want to study. Unfortunately, signal delay is not one of those conditions.
Thank you. Is there another one?
I like what you say about modules and interfaces, but what about standards? In the military world, there's all these standards that help you get complex programs to work and the bricks to stick together. And to me, it's putting the cart before the horse, not to develop standards, and secondly, repair modules, components that need to repair, should be multifunction. I give them repair modules, because you only have so much storage for repair parts, should have multiple uses, and you plug them in and to solve several problems. You know, power conversion or signal conversions.
Thank you. Yet another very relevant thing, because standards are not my area of research, but I wholeheartedly agree with you that we need standards. Otherwise, we have this really big problem in space that the Russian spacecraft, for example, cannot dock with an American spacecraft. So we do need standardization, and we should push for standardization, for sure. The other part, yes, also, I think there's been a lot of discussion inside NASA about this, that should our robots should they serve a single function or should they serve multiple functions? So there are trade-offs to both approaches that we can take. I tend to lean on the side of that we should have machinery which serves multiple functions for redundancy and so on, and the reasons that you mentioned. But yeah, I think, like I said, there's a lot of interesting conversation going around in this topic. Thank you.
Thank you. Were there any other questions?
Assuming that your bricks on the moon are going to be probably made from the local regolith, does that mean that you have to do anything special in your analogue in terms of considering what sort of material that you're using for the actual bricks?
The short answer is no, we're not. But I want to just like qualify that answer. Like I said, we have a lot of people in our university, they're doing this exact research. That, okay, we want to make lunar bricks, so how do we make these lunar bricks actually usable? Because we tried melting it, but it just becomes like very flaky or something. And so these researchers are trying to understand if we add things, regular things like epoxy, for example, or fibers, how can we make our lunar bricks more robust? And so there is research going on, so I don't want to comment too much on their research. But yeah, that this physical characteristic of a lunar brick is not part of my research. In my analog, we're trying to understand the nature of the brick through the shape. Thank you.
Thank you. Was there one more back here?
Thank you. I'm surprised you're looking at bricks. Why aren't you looking at 3D printed houses that are already built by robots in Australia, America, China, Russia, the Netherlands?
Because you're going to get it there.
I know they're not commercially viable yet in any of those countries, but surely that would be, to me, a more logical approach for building on the moon.
The word space and the word commercially viable does not work.
Yeah, thank you. I don't want to make it sound like bricks are the only solution. I think bricks are one of the solutions that can make everything happen. I think brick is one of the most promising solutions. The reason why we didn't look at large-scale 3D printers is the reason that I mentioned earlier, that in times of repairing some damage, bricks will be easier. And so that's the reason why we want to do it. But yeah, there are a lot of people doing good research around 3D printing of habitats, and I think those are equally good explorations as well.
All right, thank you everyone, and thanks. Another round of applause for Albert Rashkumar. We do have another talk coming up, but feel free to mingle, get a drink, get some food in between. Thanks.
Thanks, Olivia.
Maybe.
Yeah.